Okay, AB Calculus AB, Unit 5, Day 3, warm-up and lesson. So you can ignore number 4 for right now, but I want you guys to try these first 3 problems. And so then pause the video and then we'll go. Okay, assuming you've tried these problems. 27 derivative, we're probably looking for a pattern here. So like the original one is this, and I'd call that the 0th derivative. First derivative is positive sine. Second derivative is cosine. Third derivative is negative sine. Fourth derivative is negative cosine. Now we're back to where we were. So there's this group of 4 repeating derivatives that are going to keep repeating. So if we can take all the groups of 4 out, then you're always back to starting back at the beginning. So if we divide 4 in, there's a remainder of 3, which means that the 27th derivative is equal to the third derivative, which was negative sine x. So that's a shortcut. That's work you could show. Number 2, find the equation of the tangent line. Okay, well, you need 2 things. You need a point and a slope. So point should be pretty easy. Plug x in. So the point is 0, 0. We also need a derivative. So it's going to be a quotient rule, low d high minus high d low all over low squared. So I really like to use a lot of parentheses for this. Clean it up. 2x squared plus 2 minus 4x squared. Negative 2x squared plus 2 over x squared plus 1 squared. So that's y prime. So then we want to plug 0 into that. And we get 2 over 1 is 2. So that's your slope. And then the equation of the tangent line would be y minus 0 equals 2 times x minus 0. I'd be okay with this for your final answer and for your response. You could very easily write it as y equals 2x. That's up to you. But, whatever. Okay. Number 3 is we're trying to find the derivative. It's definitely involved a quotient rule. It's the big picture rule. But then there's product, there's trig, there's powers. So dy dx or y prime is going to equal low d high. Now d high, that's going to be a product, right? The whole thing is one big quotient, right? And the product is going to be x times derivative of sine is cosine plus sine times derivative of x is 1. Low d high minus high d low all over low squared. So now we're going to clean it up. It's going to be x squared cosine x plus x sine x plus x cosine x. Let's see. X squared x sine x plus x cosine x plus sine x minus x sine x. I will leave the denominator factored. So let's see. Those simplify. X squared cosine x plus x cosine x plus sine x all over x plus 1 squared. So I think that's about as clean as we're going to get it. All right. So there you go. That's your warm up. And today's homework is going to finally bring in some of those trig rules that we learned that haven't shown up yet. But here's just a couple more examples involving some trig and just giving you some ideas of some things you can do to make the problems easier. So, no new rules today. Just some. So, you know, go ahead and try this problem. You could be like, well, there's a quotient rule, right? And there's product. This is very similar to problem 3. So go ahead and try it. Pause the video, try it, see what you get, and I'll give you a new tip of something you could do. You can do it a little differently. Might be better. So y prime equals low d high is going to be x cubed times derivative sine is cosine plus sine times derivative x cubed is 3x squared. So that's low d high minus high d low all over low squared. Okay, so then that would be x cubed cosine squared plus 3x squared sine x cosine x. We like to put the things in front of the trig. Plus x cubed sine squared all over cosine squared. Now, I think we could clean this up a little bit. Like we could x cubed, we could factor out of the cosine squared and the sine squared, and cosine squared plus sine squared is 1. All right, so that's going to be a 1. So we get x cubed plus 3x squared sine x cosine x over cosine squared. Now I'm going to show you a different way. I mean, that was kind of the most straightforward way of thinking about doing it, but maybe we can make this easier. What if instead we treated the original problem as x cubed tangent x? Y prime equals, now you just have product, no quotient. X cubed times derivative tangent is secant squared plus tangent x times derivative x cubed is 3x squared. So your final answer is y prime equals x cubed secant squared x plus 3x squared tangent x. And this would be a totally fine answer. And that was way easier than the other one. Now, by the way, if you were to distribute this cosine squared here, guess what you get? X cubed over cosine squared is the same thing as x cubed secant squared. And here, one of the cosines cancels with one of the cosines here, and you have sine over cosine, so that'd be 3x squared tangent x. So it's the same answer. But keep that in mind when you're checking your answers on tonight's homework in the back of the book. They might have one answer, and yours might look a lot different because you kind of chose to take a different technique. And so it might not be wrong. You could try and figure out how to see if you can make one answer match the other. But, I might present some alternative versions of the answers tomorrow. Okay, next one. Now, next one, we could just do the full-on, quotient rule, which is kind of a pain. But last time we turned sine and cosine into tangent, but sometimes maybe going the other way might make things simpler. So if we change everything to sine and cosine first, then you'd be like, oh, I could and get a complex fraction, but I could simplify it by multiplying the top and bottom by cosine, and you get x cosine x plus sine x. And so you could do the derivative of this instead, which seems a little easier because it's just a product instead of a quotient. But that's up to you. Y prime here would be x times negative sine x plus cosine x times 1 plus cosine x. So y prime equals negative x sine x plus 2 cosine x. So that'd be, I think, easier, much easier in doing the quotient rule. I mean, you could try it. And it might not even look like that. So alternatively, you could do low d high minus high d low, derivative secant is secant tan, all over low squared. I mean, that's kind of a mess. But it should simplify down to something that looks like that. I mean, I don't know really how far I want to go with this as secant x plus secant cubed minus x secant x tangent x minus secant x tangent squared x over secant squared x. So we probably want to change all these secants. What we could do, we could definitely divide a secant, one secant out of everything in the top and bottom if you want. So I mean, you could write 1 plus secant squared x minus x tangent x minus tangent squared. But we could probably, and we could probably try and make it look like this by changing the secant squareds, all the secants to sine over cosine and tangent sine over cosine. So there'd be 1 plus 1 over cosine squared minus x sine over cosine minus sine squared. Anyways, I'm not going to finish it, but the alternative approach at the beginning was really nice. The way you can get good at this is trying it. Sometimes you're going to try something and it's going to make it worse. And then you're going to be like, oh, that's a bad idea. Let me try like the original. That's fine. Don't get too hung up on that. Okay. So just a couple ideas there. Now I'm going to start presenting some other calculus ideas to you. So we're going to talk about horizontal tangents, which I think we've kind of mentioned before. It's places where the graph is a flat tangent. Relative extrema. That means relative maximum or minimums. They also call these local maximum and minimums because they're just like in the neighborhood. Okay, this is very end. So FDT stands for first derivative test, which I'm going to teach you guys how that works in a second. So I don't really think you're going to need this stuff in the back for tonight's homework, but this is an introduction to it, and then we're going to take it further in future lessons. Find the x-coordinate of all horizontal tangents and determine if they locate a relative max or a relative min. So here's a function, here's some endpoints. Now, we're going to take a break from that in a second, and let's just talk about this idea a little more generically. So let's talk about horizontal tangents. How would you find when a graph has a horizontal tangent if you don't have a picture of it? Well, it's going to be where the derivative equals 0. It's flat. Now, let me just draw kind of a generic function here. And I'm not going to make it continuous. It's differentiable most of it, but not right here. So this is my function. Okay. Now, here's the deal. Here's a peak, which we call a relative max. Here's a valley, which we call a relative min. Here's another peak, relative max, valley. Here's a peak, valley. Now, peak and valley, those are very non-technical terms. This is a relative max. This is a relative min. This is a relative max. This is a relative min. And this is a relative max. Now, one of the things that you might notice is that most of the relative maxes mins have a horizontal tangent, slope of 0. But this one right here is not from a horizontal tangent, right? It's actually vertical, which means the derivative is undefined. So that's what we also need to look for relative maxes mins is undefined slopes. Watch out also, sometimes you might get a horizontal tangent, but it's not a peak or valley. not a relative max or relative min. It's more of like a plateau if we're talking in geographic terms. So we are looking for relative extrema. In simple terms, peak or valley. Okay? And so how do we do this if we don't have a picture? Okay? A peak is a relative maximum, and it happens when, let's check this out. Look, peak is going to have positive slopes on the right and the left, negative slopes on the right. All the time, right? Positive slopes on the left, negative slopes on the right. Positive slopes on the left, negative slopes on the right. If it's going from up to down, you had to be at the top of something. This is not something to memorize. It's a basic idea. Just visualize it. If you have positive slopes, that means you're going up, and then you have negative slopes, that means you're going down. If you go up and then you go down, you had to go through like a top place. So it's when f of prime changes from positive to negative in simple terms. Now, valley, or more technically, a relative minimum, happens when f of prime changes from, let's just see what makes sense. If you're going down and then you go up, got to be a valley. Down then up, got to be a valley. Negative to positive. Now this one right here goes from negative to negative, and so it's not a relative maximum because it doesn't change direction. And that's what we're going to rely on when we do the work without a graph. Now this work right here, this idea of looking at the derivative changing from positive to negative, negative to positive, that is what the first derivative test is all about. It's the first derivative test for relative extrema. Okay, and it's a big deal in calculus. So let's go back to our problem and see if we can answer the question now. Find the x-coordinates of the horizontal tangents and determine if they're relative maximums or minimums. So to find, I'm going to just rewrite the problem. So to find the horizontal tangents, we need to take the derivative and set it equal to 0. Subtract 1 from both sides, divide by 2, alpha, reference angle, when does cosine equal 1/2? Starts at 1, root 3 of 2, root 2 of 2, 1/2, 0, pi over 6, pi over 4, pi over 3, quadrants, 2 and 3. So x equals 2 pi over 3 plus 2 pi k, and x equals 4 pi over 3 plus 2 pi k. We only want the answers between 0 and pi, so that's going to be x equals 2 pi over 3 and 4 pi over 3. Those are the horizontal tangents. Now we're going to decide if they're relative maxes or mins or neither. So that was part A. So part B, a really good way to determine this is a line check. You know those things they taught you back in like first couple days of the year from algebra? It's very helpful on this. First derivative test, usually you like to do a line check. We're not going to try and figure out what this graph looks like, like actual graph. Now, we put these critical points on there. Maybe put your boundaries on there, like we've done before. Test a value. Label your line check with the y prime, so we know it's actually a y prime line check, not y or whatever. Test a value. X equals 0 would be my favorite for trig. It's going to be, cosine of 0 is 1. It's going to be positive, negative, positive. And then I like to draw these arrows on here because that means the graph is going up, increasing, positive slopes, going down, decreasing, up, increasing. This critical point right here, you can just tell from this graph, is a relative max. From this graph, you can tell this critical point is a relative min. Right? That line check Gives you a lot of good stuff. So I'm going to say there's a relative maximum at x equals 2 pi over 3. There's a relative minimum at x equals 4 pi over 3. And say at. Don't say the relative max is 2 pi over 3, because the relative max and relative min are actually the y values, which we could find if we wanted by plugging these x values back in the original function. Okay, today's assignment, 203, 1 to 10 all, 11, 21 odd, 25 and 35, mostly odds. Check your odds in the back of the book. I'll try and put the evens online if I have them available. Otherwise, just check the odds. Okay.